What we're going to do today is we're going to finish up our look at Chapter 9 on knowledge, and we're going to take a look at the theory and the idea behind connectionist networks. So we've been kind of building up to this very intricate form of knowledge representation, and you're going to see that it has a lot of things in common with some of the other ideas that we've seen previously. So specifically the spreading activation model, you'll see the idea of different connections, different nodes, this idea that activation as it goes through your semantic network spreads amongst other connections and other nodes. And but we're going to take a look at a specific version of that, which is the idea of these connectionist networks. And we're also going to see how a lot of the greatest advances that have occurred in terms of artificial intelligence over the last decade or so have used this idea of connectionist networks. So the fact that we are so close to, actually we have them, the fact that we're so close to actually having self-driving cars be the norm, where they can accurately navigate a street, accurately avoid collisions, to the point where you no longer are going to need to drive at all in the very, very near future. We're going to see how that is done with connectionist networks and how a program can actually learn these skills via just connections between different input and output nodes. And we're also going to see how perception and perceptual tasks that are tied into that idea of driving have also made great strides with the use of these connectionist networks. So the idea of letter recognition. When we started out this course, we saw that there was a very early model of how letters are recognized, and it was a template model. And this model was a very weak model. It couldn't really explain very much in terms of how we recognize letters. But we had a stronger model that could explain more of what we could do, the pandemonium model. And as you can see, again, it has this kind of idea in common with the spreading activation network, where you have certain nodes, or in this case, certain daemons that are activated, and then their activation activates others, and then that pattern is what makes that final decision in terms of what you recognize. So we're going to see one of the kind of the final iterations of this idea when we take a look at connectionist networks. So we'll once again talk about knowledge representation. How are the things that you know actually represented in your mind? So keep in mind that that is a fundamentally important question, because it has wide ramifications for how we operate. We'll take a look at connectionist networks, and I'll also mention, before we get to that, exam number 3, and we had our exam number 2 viewing time. All right, a little bit of administrative stuff before we begin the connectionist network. Exam number 3 is coming up. This is coming up in a week, so Tuesday, April 2nd. It's going to cover the following chapters and the following lectures. So it'll cover chapters 6, 7, and 9, so the 2 memory chapters and this chapter on knowledge. It'll cover the cog labs that we've gone over since exam 2. So we did levels of processing and coding specificity. And last time we took a look at that lexical decision cog lab. And then it's going to include all of the lectures since the previous exam, plus that one lecture that came before the exam. So remember, we started memory before exam number 2. Don't forget about that lecture. That lecture will also be, on exam number 3. So those are the lectures up to and including today's look at connectionist approaches. And to be very clear, today is where exam number 3 is going to end, once we're completed connectionist networks. So we are going to start up on language on Thursday, but language is going to be on the final exam. So just to be clear, so that you're studying the correct things, this is what is going to be covered on exam number 3. All right, so once again, same format we've seen with the previous 2 exams. It's going to have 2 separate sections. Section number 1 is going to cover materials from the readings that we just don't have time in this short semester to cover in class, but that are important, that you should know of. Section 2 is going to cover materials from the readings that we actually do cover in class, ideas that are specifically in the lectures and the cog labs. And because of that, section 1 is going to be worth 1/3 of your score. Section 2, 2/3 of your score. And also, section 1 is going to have recognition type questions only. So just sort of definitional, can you recognize what you've read questions, whereas section number 2 can have those types of questions as well, but we'll also have application type questions where you actually have to apply the knowledge in order to answer the question correctly. All right, so that's exam number 3 happening in a week. So we'll do that in class, and that'll be the only thing happening on Tuesday, April the 2nd. All right, knowledge representation. So we're going to take a look at how you could possibly represent this piece of knowledge that you have, which is the exclusive disjunction X or Y. So we have this piece of knowledge. We know how to operate with the exclusive disjunction, because if somebody tells you that, let's say we just finished advising season, let's say that you met up with your advisor and they said next semester you can take neuropsychology, or you can take introduction to learning. Let's say that they told you that you can take neuropsychology next semester, or you can take introduction to learning. We know what your options are that are going to fit that rule. We know that this means that you can take one or you can take the other, but you cannot take both. And we also know that if you don't take any, you're not satisfying that exclusive disjunction. So the exclusive disjunction, give you another example, you must participate in research or write an essay to earn course credit, but you can't do both. That's another example of the exclusive disjunction. That's something you might have come across in your general psychology course that you first took. And again, what that means is you can either do X or Y. So in this case, X is participate in research, Y is write an essay, and you can do one or the other in order to earn course credit, but you can't do both in order to earn course credit. So we understand this. This means that it's part of our knowledge. So how can this be represented in your mind? If it's part of your knowledge, it's represented somewhere in your mind, how is this exclusive disjunction represented in your mind? Well, one possibility is that it's represented as a list. It's represented in propositional form. So you might have just a list of possibilities that indicate whether or not you followed this rule. So for example, if no X and no Y, then you did not follow the rule. That's false. So you are not participating in research and you are not writing an essay. So you do not follow that rule. You might also have a listing in your mind as a representation that says if X, then it's true. So if you participate in research, then you are fulfilling that rule. And you could also have if Y, then true, as a list of a proposition. So if you are writing an essay, then you are also fulfilling that rule. And lastly, if X and Y, then it's false. So again, remember, you can't do both. So you are doing both. You are writing a essay and you're participating in research. That is false. You have violated that rule. So you might represent this in your mind as just a list. This is one possibility of how you have that knowledge of this exclusive disjunction. All right, so far so good? Okay. So what's another way that this might be represented in your mind? Can it be represented differently in your mind? Short answer is yes, but let's take a look at how it actually might be represented differently. And it's here that we're introducing the idea of the Connectionist Network. So a Connectionist Network, it's another model of how knowledge is represented. It's also what's known as parallel distributed processing model. So parallel distributed processing is a very powerful form of processing. It's you'll often see it thrown about if you're in computer science or if you're in engineering. A lot of times they'll be talking about PDPs, parallel, distributed processing machines. So all it means is that you're processing information in parallel. So you remember parallel versus serial. You're processing information along multiple channels, and that is just distributed. It's spread across. So parallel distributed model is what that means. And in a connectionist network, this model of how you represent knowledge is made up of units and connections. So kind of like the spreading activation model was made up of nodes and connections, this one here is made up of units and connections. And as we're going to see, it's a way of representing the knowledge that we actually have access to and that we can use. So let's take an example of this, and we'll take an example, look at perception. And perception, machine perception, has made great strides recently. You can tell machine perception has made great strides because now anytime you fill out a form, it has that little test to make sure that you're not a robot. And remember when those tests used to be very simple? Remember when they used to be just that little phrase with a couple of lines through it and people would be like, type the word that you see and it would be no problem? And now it's which of these 4 pictures does not have a stop sign in it, right? They've ramped it up. It's because of connectionist networks like the one I'm about to show you that have just gotten so good at being able to perceive these different concepts. All right, so let's take a look at how this might work. And we're going to take a look at how a connectionist network might recognize this as a number. So does anybody know what number this is? 7. Okay. So the fact is you can recognize this as being 7. If this was 10, 15 years ago, I would know right now that none of you are robots. Right now, I don't know. It's still kind of up in the air. Robots can recognize that. So how can robots recognize that? Again, we saw one model of how it is that you might possibly recognize different letters and different numbers. So let's take a look at kind of a ramped up version of this pandemonium model to see how the number 7 in this degraded, pixelated form might actually be recognized. All right, so this is the connectionist model, visual representation of the connectionist model that can recognize different numbers. So you'll see that out here, it has these outputs, and depending upon which one of these is the most activated, that's how it indicates the number that it's seeing. So let's zoom in on this ever so slightly, just to kind of get it up there a little bit more. And this is the basic idea of the connectionist network. You have these different nodes, you have these different connections, and all the work is done via the interaction of these nodes and connections. So let's break that down a little bit, see what we're working with here. We got units, we got connections. The units, there's 3 distinct type of units. We're going to take a look at all of them. First, we're going to start with the input units, and these are the ones that are activated by the stimuli. So the input units, we got them right there. Those are the input units, and for this particular model, they're only showing you, what do we got here? 3, 6, 8. They're only showing you 16 input units. You see these 3 little dots here telling you that there's input units missing. That's because in this case, there's actually 784 input units. So for that image that I showed you of that 7 has 784 pixels in the image. There's literally 784 individual dots in that particular image, and each of those dots is linked to an input node here that'll let you know whether that dot is on or whether that dot is off. And that's all that it does. So we got 784 input nodes that just take information from the stimulus, and that's where that information is put into the model. That's where it's input. And again, in this case, we got 784. Each of these indicates whether a pixel in that image is either on, so it's white, or it's off, it's black. All right, so that's the input units. Those are the ones that are actually activated by the stimuli. At the end, we have the output units. The output units are the ones that actually communicate the information. So the output units are those ones right over there. And the output units are the ones that give the output. They're the ones that communicate the information. So in this case, the output is read by the person that's operating this network to be the one that has the highest level of activation. And in this case, that would be the brightest unit here, which is 5. So this output would indicate that this connectionist network thought that it saw 5. So that would be the output of this connectionist network. And notice, we'll go back all the way to the beginning of the semester. This is a physical symbol system. So this is a symbol system that is that has designation. You can designate stimuli, put them into this system, and it's got interpretation. It's got an output that somebody can look at and say, oh, this machine saw a 5. So we got inputs and we got outputs. So next is the important, massively important level, which is the hidden units, the middle levels. And this is where we get this processing of information. So we have the input units, we have the output units, and in between, we got these hidden layers here. So this one actually has 2 hidden layers, and those hidden layers kind of form the interconnections between different units in this model. And those hidden layers are where a ton of the work is done in any parallel distributed processing model in any one of these connectionist networks. All right, so that's the buildup of the units. You got your input units, you got your output units, you got your middle units in between. This is a connectionist network, so clearly we need connections. And the connections are simply the links between the units. And importantly, these connections can be differently weighted. And that's where the power of this network comes from. It comes from the fact that, number one, there are tons of connections. And number two, those connections are differently weighted. So in this representation here, you can see tons of connections. So between the input level and the first hidden layer, we got tons of connections. Between the first hidden layer and the second hidden layer, we got tons of connections. Between that last hidden layer and the output layer, we got tons of connections. And these connections all have different weights. And in this case, the weights of these connections are shown by, first off, the color of the line. So if the connection is blue, a bunch of stuff going on. If the connection is blue, that means if one input is activated, this connection will activate this input. So blue connections are positive connections. If the first unit is activated, if it's connected with a blue connection, the second unit is also going to get activated. The other types of connections here that you'll see are red connections. A red connection is inhibitory. If the first node is activated, then that means that it'll actually inhibit the activation of that second node. It'll actually turn the volume off on that second node. And then the other thing to notice is that there's different thicknesses to these connections. That's a visual representation of the strength of the connection. So the thicker the line, the stronger the connection. So if this node gets activated, then this node over here that's attached by a thick blue line is going to get really a big increase in its activation. But if this same node is activated, look at this thin little blue line here, this node is going to get activated, but just a little bit more. So the connections can either be positive or negative. They'll either increase or decrease activation. And they can either do that by a lot, or they can do that by a very small amount. All right, and that is the entirety of the model. So what we're going to do is we're going to go back to this simpler example. We'll see whether you can recognize the number 7 in a bit. But let's go back to this simpler model here, the simpler example, and see if we can represent this information here, to see if we can represent these 4 cases here in a connectionist network that through units and activations can actually achieve an understanding of this exclusive disjunction. Can actually achieve that understanding that you need to have X or you need to have Y. If you have none of them, you're not following the rule. And if you have both of them, you're not following the rule. All right, so let's take a look at this simpler connectionist network. All right, so for this connectionist network, we got our input layer right here. Our input layer has 2 units. Unit number 1 signals the presence of an X. Unit number 2 signals the presence of a Y. So when the inputs come in, if there's an X, this input will get activated. If there's a Y, that input gets activated. We got hidden layers. We got 2 levels of hidden layers. So those are the hidden units right there. And then we have our output units over here. And those output units will either be true, you followed the rule, you have X, or you have Y, you have at least one, but you don't have both, or it'll be false. You violated the rule. You either didn't take any, or you took both of them. You violated that rule. And then the last thing we need here is we need connections. And there are the connections, and there are the weights for the connections as well. And I think we got a couple more weights here. So we have the connections between the units. We have the weights of the connections. So this unit, when it's activated, sends +1 to this unit over here. This unit, when it's activated, sends +1 to this unit over here. We got negative connections. This unit, when it's activated, sends -2 to this unit over here, for example. And then the last thing we have here is these numbers here indicate how much activation each of those units needs before it can fire, before it can send its signal onto the next layer. So this unit over here only needs 1 amount of activation. This unit over here needs 2 amount of activations before it will fire and send its message to the next layer. All right, and just to kind of highlight these negative units there, we'll keep them in, we'll keep those in dotted lines there just to sort of visually highlight that. And then the last thing that we're going to do for this is we are going to set that false output as activated by default. And this kind of makes sense to have it at that default location, because if you don't have X and you don't have Y, well then clearly it's false. So we're going to start off with that being activated. We're going to start off with that being false. All right, so let's take a look. Suppose you have X. If you have X, that means that you have followed the rules. If somebody says you have to either have X or you have to have Y, but you can't have both, and you have X, you have followed the rule. So let's see for that input of X, if we get the condition true, which we know to be true. So let's follow it in this model. So first we start with the input phase. Input phase activates X. That's what it means by saying you have X. So in the input, X gets activated, Y does not get activated. Because of this activation, this unit is going to send 1 unit of activation. It's going to send 1 amount of activation to this node over here. It's going to send 1 amount of activation to this node over here. So right now, this node over here has 1 level of activation. This node over here, this unit over here has 1 level of activation. That is enough to activate that unit. It is not enough to activate this unit. So what happens now? The processing continues. This unit gets activated, sends 1 unit of activation down here. This unit requires 1 unit of activation. It gets that amount of activation. So now it is going to send its activation. It sends 1 unit of positive activation up here to true, turns on that unit. It also sends 1 unit of negative activation down here to false, turns off that unit. And you can see that through the connections and through the weights, we end up with the correct result, that it actually is true. We actually, when we have X, it pops up as true. The network, in this case, made the correct decision. Was that example clear? So far, so good? Yep.
So if it's sending 1 to true and 1 to false, then how do you determine that it's true and not false?
If this and this was activated?
Yeah, because didn't you say that it sends 1 to both?
It does. The key there, though, is this connection here is negative.
Okay.
So it sends 1 negative unit. It actually turns off the false node. So you're absolutely correct. If this was the case, you'd be confused.
Right.
And as we're going to see, especially at the beginning parts where a network is learning what connections to have, it will be confused. And you will say something like, suppose you have X. and the network might say false. And then you'll see how it gets corrected as it goes through. But you're absolutely true. If this output was here, it would be ambiguous. But this -1 turns off that node, leaving only true, so we got the network being correct. All right, next example. Let's suppose that we have y. So we don't have x, we don't have y. We know that this conclusion should be true. So once again, let's see how the network handles it. This time we don't activate x, because we have no x. We activate y. Y gets activated, sends one amount of activation to the center unit here, sends one amount of activation to this unit over here. This unit needs 2 levels of activation to activate, so it stays dormant. This unit over here only needs 1 level of activation, so it gets activated. So now it's going to send its message along, sends 1 unit of activation up to this connection to this unit over here. This unit needs 1 unit of activation in order to activate, so it activates. And then once again, it sends out its signal +1 to the true unit, -1 to the false unit, turns on the true unit, turns off the false unit. And once again, we have the network deciding that the conclusion is true. And once again, the network is correct. So that was for when you have y. So we've taken a look at when the conclusion should be true. Now let's take a look at when the conclusion should be false. So let's suppose that you have x and y. So remember, this is the exclusive disjunction. You can have one or you can have the other, but you can't have both. It's kind of like another good example is if you're being offered dessert as a child and your parents tell you you can have pie or you can have cake, but you can't have both. You know you got to take one or the other. You know that this is a violation of that rule. So let's suppose that you have both x and y. So in this case, you've taken x and y. The conclusion should be false. When we go through this network, this false node should stay on. So let's see if it does. So we got x this time, and we have y. Both of those nodes get activated. Both of them are going to start spreading their signal. X sends 1 amount of activation to this unit over here. That activates that unit. X sends 1 unit of activation to this node over here. Sorry, to this unit over here. Doesn't quite activate it, right? So this one is at level 1 right now. But this is the first time that y is also sending a level of activation. So now finally we got 2 amounts of activation being sent there. That one gets activated. We also have y sending 1 level of activation down to this unit. That one gets activated as well. So now we got 3 units in the first hidden layer being activated. The top unit sends 1 level of activation down to this unit over here. The bottom unit, I believe, also sends 1 level of activation to this unit over here. But importantly, this time, this middle unit is activated. And it has a very strong negative connection to this unit here. It sends -2 units of activation to this unit over here. So now we have 1 unit of activation plus 1 unit of activation is 2, minus 2 units of activation is 0. This does not get activated. So this one stays dormant. Nothing happens here to change the situation. This one is activated by default, and we have our network saying that the result is false, and the network is correct. All right, we got one last example. So you have no x, no y. So you didn't choose x, you didn't choose y. Is there a question?
Yeah, I understand that false is, you said it was activated kind of by default, but why, I guess? Because it definitely makes sense how it stays false with both of them there.
Mm-hmm.
But I guess just why is it already false?
Well, the simple answer to that would be because it works for the model. Yeah, it does work. So one of the things about these models here is that you can set nodes to already be, units to already be activated or not activated. You can set them to require certain levels of activation. You have a lot of freedom in the unit, so in setting the units and the connections. So the fact that we set that one false to default beyond is partly the uninteresting answer is because it works. It works that way. It covers all 4 cases. The sort of more kind of logical answer to that is that usually the default is that you don't have anything.
Yeah.
So if somebody says, you can take either, neuropsychology or, intro to learning, typically you're sitting there without either. If somebody says you can either have pie or cake, it's very rare that a person says, oh, I got a piece of cake right here in my pocket that I just carry around. So usually it's the default that it's off. So that's why it's off in this model as well.
Okay.
All right. So lastly, and this is the uninteresting case, which we actually just kind of covered here. If you have no x and you have no y, your conclusion should be false. So somebody says you either have to have x or you either have to have y. You got neither. The conclusion is false. In this case, there's no inputs coming in whatsoever. Because there's no inputs, this doesn't get activated, this doesn't get activated. No signal gets sent through the connectionist network. So nothing gets activated. And because of that, this doesn't get turned off. And your conclusion is false. And once again, we see that this network is correct. So in this case, this one network, this one series of connections here, based on the input, has given us the correct output for all 4 possibilities for this exclusive disjunction. So it's quite possible that in our minds we have this list representation where we just go down the list and say, what situation are we in? Oh, we're in this one. The conclusion is true. But it's also quite possible, and it works, and it kind of captures what we know, that we might have our knowledge represented like this in this connectionist network, where once again, depending upon whether X or Y is activated, we will get, after all this processing, the correct answers. All right, so can this information be represented differently in your mind? The answer is yes. This information here is the same as this representation here. They're represented differently, but the knowledge in your mind, you have the same knowledge in that list as you do in that series of connections between different units and different connections. All right, so any questions on that before we go to a slightly more complex model? All righty. So let's take a look at a little bit more of a complex model. So this is going to be the knowledge of living things. All right, so we're going to up the complexity just a little bit here. And just so you know, how many calculations are needed in an actual connectionist network. So when I was doing my graduate work at the University of Toronto, they were a hotbed of connectionist research in psychology. And they actually, if you were in that lab and you're working on that lab, you would book time with the supercomputer that we had at the university, because you needed something that could process pentaflops of connections, right, in order to do these models. So you had to book time with our supercomputer, which at the time that they got it was one of the top 100 computers in the world in terms of processing power. So think about that for a second. They were in the top 100 of every single computer in the world. And you still have to book time so that you can go in there. And when you're doing your connectionist network and you set it up on these learning trials, you would set it up on Monday night and you would come back sometime on Tuesday. And this supercomputer, top 100 in the world, would be spending hours processing it. So you know how sometimes you try to install something on your computer and you see that little bar going across? All right, imagine how many connections are needed if you have one of the top 100 powerful computers in the world, and that bar still tells you approximately 16 hours before it installs. So tons of computations once you start getting into visual recognition and other more complicated things. So let's up the complexity just a little bit right now and consider knowledge of living things. So how can we represent things that we know? So we saw this in the Collins and Killian's model, but now we're going to see how it could be represented in a connectionist network. And once again, it's important to remember that we might have a list representation. So that used to be the way that people would think that we represented our knowledge. And, you know, we might have just lists of things we know about canaries. A canary can grow, a canary can move, a canary can fly, it can sing. We might have things we know about robins. Robins can grow, robins can move, robins can fly, robins can sing, etc. So how could this knowledge that we definitely have be represented in this connectionist network? So this one's going to get a little bit more complicated, but just kind of give you an idea of what this could look like. You would have the concept level here. This is almost like the input level. And then you have different hidden layers, once again. So you have your units here that indicate whether you're dealing with pine, oak, a daisy, a canary, a sunfish, or a salmon. And then you have these hidden layers that can include what can be labeled as relation units, and also as property units, and then also as representation, and then a second hidden layer over here. So if we had this connectionist network, where you have your inputs of these are the categories, and you have your outputs here of what properties do they have, how can this network represent the information that we have in our mind? All right, so let's start off with the idea that a canary can grow. If you know that a canary can grow, if you know that it doesn't just start off full size, then we have that representation somewhere here. So you might start off with activating canary. As soon as somebody says canary, your input activation starts, right? So when somebody says canary, this input unit, this input level activates and says, oh, canary is recognized, canary is activated. That can grow. So it asks, canary can. You can think of this as your second level of activation. It's asking you, canary can. So you have that second level of activation. And you want to make sure that that last level, grow, is also activated. So when somebody says canary can, your network of activation, your connectionist network, in order to represent this knowledge, should have that output of grow activated by the end of it. So in this case, we could link canary to a representation unit that it activates. That representation unit might be linked to a hidden unit. That can relation might also be linked to that hidden unit. And then when that's activated, that can get linked to grow. And then this activation here, this pattern of activation, would represent in your mind the idea that a canary can grow. What about a canary can do other things, such as a canary can move? Well, in that case, we already have these connections here, that a canary can, representation, hidden line, go to grow. A canary can, hidden units, go to grow. But now we also have to activate move, because we also know that about canaries. Canaries can move. So in this case, we want to activate move as well. And we might be able to do that using that same hidden node and just link that down to move as well. So we're kind of building our model. We're kind of building the connections in our model to try to have this connectionist network that represents our knowledge. So now we have those connections. And we continue on. A canary can fly. So we continue to build our knowledge about connections. About canaries. And this is actually one of the things that connectionist networks are very, very good at. And this is one of the reasons why connectionist networks kind of exploded in popularity and in terms of the possibility of helping to understand human cognition. Because unlike other computer programs, connectionist networks operate a lot like our minds seem to operate. So connectionist networks learn the same way that we seem to learn. Connectionist networks make the same mistakes that we tend to make. Connectionist networks learn quicker after they have connections already established in them, right? So it's the same thing with us. The more you learn about canaries, the more you can learn about canaries. And it's the same thing here because it takes advantage of connections that are already existing and it just has to build upon those connections. So we can continue to have these representation and hidden units and build these things that we know about canaries. So a canary can sing, we continue to build those connections. All right, Now, what about robins? So now we have robins. And we want to make sure that we can also activate robin information when we come up with a phrase like robins can. So we activate robin, we activate can, this is the input unit, we activate that relation of can. And now we can take advantage of some of the things that we know about canaries and use those previous inputs to immediately represent that a robin can grow, can move, can fly, can sing. So this is another indication that kind of mirrors how humans learn, right? That first bird you learn about, there's going to be a lot of new information. But as soon as somebody else is like, oh, a robin's a bird, you can be like, oh, I bet they fly. I bet they sing. I bet they move. Because you already have those connections made in your connectionist network. All right, robin is. So say we have things, now we're changing the relation. Not a robin can, but a robin is. So now we have this relation activated. And as you can see, I mean, the point here is that it's just a series of connections that has this parallel activation that goes through it that is linked to all of these different output units. And it's the pattern of activation that determines what is represented in your knowledge. So your knowledge is not represented in a single place. There is nowhere that you really have this canary is stored. It's stored across, spread across this connectionist network. So if you were to say, well, where is canary is, living? Where is that exactly stored? It's not stored anywhere in particular. It's stored as an activation pattern across this entire network. All right, so that's your somewhat simpler example. And you can imagine just how incredibly complex this is going to get, because we've only touched on 1, 2, 3, 4, 5, 6, 7, 8 things about canaries and robins in this network, and we haven't even looked at any of the other concepts. You can imagine what the connections get to be like in a fully fledged connectionist network. So when somebody asks you, can a canary grow? This is the activation that occurs, and if this output is activated, then you will say, yeah, a canary can grow. If somebody says, is a canary yellow? Once again, canary activates, that spreads the activation through these connections. And notice that, in this case, salmon is not activated. So that's how we know a canary is not a salmon. But yellow is activated. That's how we know a canary is yellow. And so on and so forth. The robin is red, has that spreading activation. All right, any questions on this before we get to a more realistic, kind of fully fledged model? Mm-hmm.
So would like the property column represent like our knowledge?
The property column in this case would represent the properties that these concepts have or could have. So you do have this kind of level of this connectionist network would indicate that you have an understanding of what pretty is. You have an understanding of what red is. So we've kind of like pulled back because you would have, and that's one of the things that can drive you a little, into the inception kind of realm of this. You would have a connectionist network that tells you what red is. So this unit right here might be a completely separate connectionist network, right? This unit of is might be a completely separate connectionist network. But in this kind of representation, these are your outputs. So you have the concept of grow, you have the concept of sing, and what this is representing how you connect these concepts to these concepts, so that if somebody said, does a canary have roots? You would activate what you know about canary, take a look at your outputs and say pretty, living, yellow, grow, move, fly, all of those are activated. Look, roots down here, not activated. So I know these things about a canary, but I know it doesn't have roots. So that's kind of how your knowledge of this might be represented. All right, any other questions about connectionist networks? All right, so let's ramp it up a bit. Let's take a look at this actual model here to see how some of this actually is done. So actually is done if you were trying to get a visual recognition connectionist network going. How might that work? Let's take a look behind some of the programming for this.
In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations. We only have influence on the weights and biases.
Okay, so right off the bat, this is the beginning of this connectionist network. And as you can see, what usually happens is you just set up the input units, you set up the output units, you set up the connections and the weights for the hidden units, and then oftentimes they'll just randomly set the weights for the connections. And they will put an input through this connectionist network, and that input will start spreading through. It'll start activating nodes. Nodes will activate or deactivate other nodes, and it'll pop out here, and it will be, this network here is confused. So they showed it this, and this network in its current state says, well, I'm kind of confused. That's either a 3 or a 6. And in reality, it's a 2. So this is kind of like when you're teaching a child, you know, the alphabet or the numbers, and you hold up a number, and you're like, what number is this? And they're like, I don't know. It's either a 3 or a 6. And you're like, no, it's a 2. So it learns. You have to teach these networks. There's no human being in the world that can just look at this and say, oh, this should be a plus connection. This should be a minus connection. That's why we need the supercomputers in order to do this so that we can build these networks. But what we do is, or what they do is they train it. So they'll show it a 2, and they'll say, what's the output that comes out? And if it's wrong, right, this is the output that it should have. It should have, ideally, only 2 activated. Everything else should be at 0. If they then say, what's the difference between this versus this, and they use that information to change the network.
But it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we wanted to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer.
All right, so we're not going to get too much into the actual mathematics of this. I just wanted to show you kind of how this actually goes through and gives you that output. So once again, on that example, you saw that when the 2 got activated, when the 2 was shown, each of these input layers got activated. They sent their activation. These hidden layers got activated, so the black ones are the ones that are not activated. The white ones are the ones that are massively activated. The gray ones are the ones that are only a little bit activated. Depending upon the weights they need for activation, they sent it forward to other units. Those units then sent it forward to the output units. And the programmer then takes a look at the output units and says, is it right? Is it wrong? And if it's right, the network stays as is. If it's wrong, what they do is they send a program backwards through the network, change these links. They'll change the weights of the individual links and then run it again. And this was what the supercomputer would be doing for 16 hours, because they would program in maybe like 1,000 trials of this and do that correcting of the network every single time that it occurred. So this is basically what is going on right now when manufacturers are working on cars that can drive themselves. This is basically what they're doing. So when they are working on these cars that are driving themselves, when they're working on these cars that will allow you to just sit back while they navigate the road, what they're doing is they're using, in a simplified version of this, they're using these connectionist networks. And they're sending this car out into some sort of driving environment. And if that car navigates that environment correctly, if it stops at the stop signs, if it doesn't run over the pedestrians, if it doesn't jump the curb, if it does it correctly, then the network that they have, that input network that comes in the input through the driving sensors and the forward-facing cameras, that input network has those connections to the output network. Pedal on the brake, pedal on the gas, turn left, turn right, turn signals on. It has all of those outputs, and it links inputs to those different outputs. So all they do is kind of let this car drive, and when it jumps the curb, they say bad car, like they said in the other one, bad network, and they look at the output, and they say, all right, at that point, gas was not required, brake was required, turn right was the wrong answer, turn left was the wrong answer. So all they do is they say, in that case, we're going to increase the output of brake, we're going to increase the output of turn left, and then we're going to run it again. And this time it goes again, and this time it runs a stop sign, in which case they say bad network. And then they take a look and they say, all right, when this activation came in, we needed brake. And they just keep doing that and doing that and doing that. And eventually, you get yourself a very good car that can drive, that has all those hidden units, all those input units, output units, hidden units. You come up with a network that drives, honestly, they've done the research, better than humans, right? So there are fewer accidents per mile for the programs that are the self-driving cars than there are for actual humans. Mm-hmm.
So did they start with like the whole, how there's some cars that can like parallel park for you?
Oh yeah.
Was that like their starting point? Like if we can get this car to parallel park you, then we can maybe get it to drive on its own?
That's a very interesting question. One of the things that you will become apparent if you ever delve into this research is that this is clearly a multi-billion-dollar idea. So if you were to call them up and say, hey, what's your network that you're using? Can I have that for science purposes? You get a very hard no, that they're not going to let you take a look at it. So in terms of the parallel parking, because I remember that was one of the early ones that they had in the commercials where they're like, you drive up next to it, you let your hands go, and the steering wheel starts doing all these things, and all of a sudden you parallel park. I wouldn't be surprised at all if that actually was a connectionist network. And notice that is a much simpler connectionist network. So parallel parking, I remember when I was learning how to parallel park, there's like 3 or 4 well-defined moves that you do. So you line up so that there's a certain distance, and you have their tail light in that little triangle window in the back of your car. You then, do one, I think it was like one turn, and then as you hit 45, you then go the other way. So there's only like maybe 8 steps to parallel park. In just the same way that I was able to come up with the X or Y connectionist network because there's only 4 steps, it was probably a lot easier for them to program that parallel parking connectionist network where it would actually be successful at parallel parking. And it was probably a connectionist network, but a much, much simpler connectionist network because it was such a well-defined situation for parallel parking. Nowadays, you have cars can do a lot more difficult things. And it's interesting that the less well-defined a problem is, the more difficult it is for a computer to actually implement that. And that's the way that we work, as well. So, for example, my daughter is 8 years old right now. And there were a lot of things that were really easy to teach her. So, for example, math is really straightforward because it's got rules. right? You got a 5, you want to add a 6 to it, that equals 11. That's a very well-defined, straightforward rule. What's challenging nowadays are social conventions, right? And those are challenging a lot of times for adults, right? So how do you respond to somebody so that you don't sound mean or aggressive, right? That's a difficult, poorly defined problem, and that's where she currently is at. That's that kind of challenging moment. And as these connectionist networks get more powerful and powerful, basically they're going to be able to handle all these poorly defined problems. And one of the big questions in automated cars right now is what kind of a decision are they getting programmed to do? So one of the super cool things that pops out of a connectionist network like this is that sometimes the model will end up doing things surprisingly that you never taught it to do. So oftentimes it'll have skills that you didn't think it should have. Oftentimes it will come up with outputs that you didn't teach it, but all of a sudden it's doing this other output thing. So one of the big questions in terms of automatic driving cars is what will they do in certain moral situations. So you can teach a car not to run over a pedestrian, right? You can teach a car not to jump the curb. You can teach a car to navigate down a road, stop at a stop sign, slow down at a yellow light. You can teach it all those things. But right now, what they're wondering is what kind of moral decisions might these driving cars make? Because if you are about to run into an elementary school child, right? If you're about to run into an 8-year-old child that is crossing the road, so this child just ran out right in front of the road, and now you have the choice. You got no time to brake. You got to swerve, right? And you either run over this 8-year-old child or you swerve and you run over this 40-year-old individual. What are you going to do? And human beings have a hard time answering that. And there are studies in judgment. We'll see some of those. You'll read about some of those studies where human beings themselves don't know how to do. Or don't know exactly what to do. One of the most researched conundrums in psychology. There was two big ones. One is the trolley problem, where a trolley is about to hit like 5 people. And you have the decision of whether you switch to another lane or you stay on this lane. But if you switch to another lane, there's a person that you are going to kill. So you have to decide which one are you going to do. And there's all sorts of factors that go into play, whether it's an active, choice to switch and kill the other person, whether it's a passive choice to switch. Do you value one life less than, a bunch of lives? The other one that was really, really well, that's really well researched is the one where there's a cruise ship that is sinking in the ocean, and 600 people are on that cruise ship. And you can either, A, go with a plan that is guaranteed to save 200, and 400 will die. So you're the Coast Guard, and you have to make this decision. And you're like, either we send this airplane or this rescue mission. And this rescue mission, guaranteed, will save 200. Guaranteed, 400 will die. Or we have Plan B. And Plan B has a 1/3 chance of saving everybody. And it's got a 2/3 chance that everybody dies. So notice that mathematically those two are equivalent, right? In both cases, on average, 200 people are going to die. And the choice that they ask people is, which one would you yourself choose? Would you make that decision to save 200 people and doom 400 to their deaths? Or are you going to gamble with lives and say, your 200 guaranteed survival, I'm willing to gamble you for 600 survival, but most likely 600 dead, right? Because 2 out of 600 are going to die. Those are moral decisions that have been studied in humans. People are wondering, what are going to be the moral decisions that are going to happen with these driving cars? Because just the same way that oftentimes we're taught skills without being taught the morals, The same thing is being done with cars. Mm-hmm.
As a result of the networks developing kind of their own decisions, would it be different depending on like different cars' experience then?
Yep.
So a car could, just like a human would make a different decision.
Yep. So the other thing about the networks is that they can build up, you can build up a network and you can teach a network to do certain things, but no two networks are going to be the same. So you can copy a network, but if you teach a Ford how to drive and you teach a Volvo how to drive, and they both drive very successfully, there's no guarantee that those two networks are going to even look the same, but they'll both be able to drive. So yeah, I mean, these kind of questions are one of some of the big, huge questions that these researchers are asking. All right, so that's where we're going to end it for today. Next time, we're going to show you, I wanted to show you this, but we ran out of time. We'll take a look at a connectionist network that can do something not as complex as driving cars, but just play Super Mario World. And that will be our wrap-up of Connectionist Networks. So other than that, we are done for the day, and I'll see you all next time.